Every summer, the livelihood of over 500 million people hangs on a single meteorological event. 60% of India's agricultural land relies entirely on the arrival of the southwest monsoon. Fluctuations in heat and atmospheric pressure drive the transport of billions of tons of water across the subcontinent. This chart shows the chemical composition of the atmosphere powering that engine. Nitrogen and oxygen account for 99% of the volume. This isolated sliver represents carbon dioxide, which makes up just 0.04%. By tracking how these specific gases transfer heat within the lowest layer of our atmosphere, the troposphere, we can build a mechanical model. This model tracks how normal weather patterns operate and identifies the specific conditions that lead to anomalies. The monsoon operates on the predictable laws of fluid dynamics. Like any highly tuned engine, changes to the chemical inputs can lead to structural failures in the system's output. To understand the subcontinent, we start with a single shoreline. The physics rest on a property called specific heat capacity. Solid land masses absorb and release solar radiation rapidly, while liquid bodies of water require much more time to change temperature. As the sun rises over the coast, the land heats quickly. The air immediately above it absorbs that thermal energy, expands, and rises. This upward movement creates a localized vacuum at the surface, a zone of low pressure. Nature seeks equilibrium. To fill that empty space, cooler, denser air from the adjacent high-pressure ocean rushes inland. We experience this horizontal transfer of fluid as a sea breeze. At sunset, the mechanics reverse. The land radiates its heat away rapidly and cools down. The ocean, however, holds on to its stored thermal energy, remaining relatively warm. The thermal gradient has flipped, and the pressure systems follow suit. High pressure sits over the cold land, and the wind reverses direction, flowing back out to the low-pressure sea as a land breeze. Wind is fluid moving from high pressure to low pressure. This physical rule dictates weather on every scale. When we apply this micromodel to the entire Asian landmass in early June, the forces multiply. During the summer months, intense solar radiation bakes the Indian subcontinent. Millions of square miles of heated air expand and rise simultaneously, creating a massive low-pressure void in the atmosphere. To the south, the Indian Ocean absorbs the exact same sunlight, but disperses the heat deep into its waters, remaining relatively cool. A high-pressure zone anchors itself over the sea. This pressure differential creates a planetary-scale vacuum. Billions of tons of dense, moisture-laden air are dragged continuously from the ocean, rushing north to fill the void over the landmass. This sustained fluid transfer is the engine of the southwest monsoon. From the ground, this thermodynamic equation manifests as towering walls of dark storm clouds rolling over coastal cities. The Indian monsoon operates via the exact same mechanical forces as a gentle afternoon sea breeze. These wind currents do not travel unobstructed across a flat plain. They are forced to interact with the physical geography of the continent. As the moisture-heavy winds rush inland from the Arabian Sea, they collide with the Western Ghats, a steep mountain range running parallel to the coast. The air is forced upward. As it gains altitude, atmospheric pressure drops and the air cools. The moisture it carries rapidly condenses. This process, the orographic effect, triggers intense precipitation. Over 11,000 millimeters of rain fall annually on this windward coastal strip, creating thriving, water-rich ecosystems. When the air mass clears the mountain peaks, it has been stripped of its moisture. This dry air sinks back toward the surface. As it descends, it compresses and warms, preventing cloud formation and creating an arid rain shadow on the leeward side of the range. Topography acts as a mechanical barrier, dictating the unequal distribution of rainfall across India. These pressure zones and towering storms are confined within strict vertical limits. Atmospheric water vapor and weather phenomena are trapped in the troposphere, the lowest layer of the atmosphere. Immediately above it sits the stratosphere. Lacking the moisture of the troposphere, it acts as a stable, weather-free lid containing the ozone layer. Aviation infrastructure relies on this atmospheric boundary. Commercial aircraft climb past the troposphere to cruise in the stratosphere, physically bypassing the violent thermodynamics below. The boundary between these two layers separates the turbulent environment required for agriculture from the stable vacuum required for modern transit. The stability of the monsoon engine relies on a precise chemical balance. Carbon dioxide possesses a specific physical property. It traps infrared radiation that would otherwise escape into space. As emissions increase trace gases, excess thermal energy is injected into the troposphere, warping the temperature gradients driving the subcontinent's pressure systems. Adding heat to a fluid dynamic system adds velocity. The engine processes unregulated spikes, resulting in concentrated downpours over Punjab. In 2025, Punjab experienced the mechanical failure of this system. A monsoon current carrying record moisture collided with Mediterranean storm fronts known as Western disturbances. This atmospheric anomaly was compounded by failures on the ground. Aging embankments collapsed under the pressure, while residential encroachment into natural floodplains eliminated the landscape's ability to buffer the excess water. The result was a mechanical failure of the region's watershed. The Satluj, Beas, and Ravi rivers swelled past their physical limits, submerging entire communities. The atmosphere functions as a sensitive fluid dynamics engine. Altering its chemical composition dictates the mechanical outputs of the entire weather system.